going tonight. I'd like to introduce Pat Swords from Project Management. Pat's a chemical engineer and a bit of an ATEX guru, and he's going to speak to us tonight about
Yeah, so I suppose just PM group, as we now call ourselves, are actually. So we're something like 2,100 or 3,000 employees worldwide, and we do a lot of pharmaceutical engineering and food engineering. So we don't do residential buildings, we do more complex industrial projects, and that would be where my experience predominantly lies, which is where most of the ATEX issues lie too. And I'm a chemical engineer and a professional process safety engineer with the IChemE, and I've worked in PM group for a good long time, more than I want to say. But I've also spent a lot of time abroad dealing with bringing in the EU's legislation into the various member states. And so a lot of my ATEX experience is as much outside Ireland as it is inside Ireland. So it's a bit different in that respect. The next one is the standard sort of warning, is that there's a well-known phrase that for every complex question there is a simple answer that is almost invariably awfully wrong. So as usual, this is a complex subject. We'll give you an overview tonight, and it's a question of getting the principles right. But it is important that there is a lot of complexity to it, and there's more to be learnt than what I will be doing here tonight. So what I like to do is that there are actually two strands to this ATEX, which is the French for atmospheres explosibles, or explosive atmospheres. And they run in parallel, and one is doing with worker safety, and the other one is with equipment and the type of equipment you should be using. So I'll discuss that. And then we have two types of hazards. We have flammable hazards and we have dust explosion hazards. But the real thing is to be aware is that there are principles of prevention in order of priority. Is that we need to avoid the formation of potentially exposed atmospheres. We have to do that first. So always go and think of these steps. Avoid it. Don't have dirty plants. Don't be using bucket chemistry with cans of solvents going around the place. And only when we can't avoid the explosive atmosphere do we take the next step, which is to zone it and to put in the electrical protection and the non-electrical protection. And then if we can't eliminate all the ignition sources, and sometimes we can't, we put in measures to vent explosions or suppress explosions to mitigate their detrimental effects. And then sometimes to stop explosions spreading from one piece of equipment to another, or ripping through a sugar plant like in Atlanta, where they had the biggest loss of life in an industrial accident in the United States in the last 20 years when a sugar plant blew up there. We put in measures to stop the propagation of explosions. And no matter how good an engineer designs it and puts in all the gizmos, unless people have the organizational measures and the management to go with it, they're not going to work. So it should be a little, yeah, just a little simple video just as a warm-up. I think you've seen these NAPO videos before. They're always quite good for giving a little bit of training. Toolbox talks. No. Has it stopped? Oh no. No, the computer's. Anyhow, the computer's not doing what it should be doing. But basically, oh, there he is. He starts welding. He sets on fire the rag, knocks over the bottle. Suddenly things escalate out of control, and the whole factory is burnt down. So anyhow, I mean, these are the things with, you know, lack of awareness, lack of control. Things can go horribly wrong, and then we have to call in the insurance company to pick up the bill, or the medical staff. So anyhow, if we talk about the legislation, ATEX doesn't exist on its own. You know, the first thing is that we have the Framework Safety Directive, and then we have a second directive, which is the first ATEX one, came out in 1994, though it's actually been updated, and a new one will come into place in about 18 months' time. And that's all about equipment and the certification of equipment. And then there is one on the worker protection, which came out at the end of 1999. So, but it comes down to the principles of prevention, you know, which is avoiding risk, combating risk at source, doing your risk assessments, adapting to technical progress. So the whole idea that we would have a plant using open containers of solvent and open vessels that wouldn't be sealed, or that we would have dust lying around the place, like plants were designed back in the 70s and 80s, is no longer acceptable. And that comes back to, you know, that we have to adapt to technical progress. We can actually design a plant processing flammable solvents or the likes of alcohol, which has no external zones to it because it is so well sealed. So you always had to have a safe plant, and the Framework Directive and the jurisprudence with it strengthened the requirements for risk assessments and the implementation of protection measures that are reasonably practical. And this ATEX Worker Protection Directive, it's only one of 19 daughter directives, and it's just giving you the specific details with regard to explosive atmospheres. You're well familiar with the other daughter directives. They're like the construction site regulations and safety ones. They're to do with chemical agents, they're to do with noise at work, they're to do with biological agents and so forth. But the principles of this are applicable globally, so that you may not have this ATEX 1999-92 all written into somebody's legislation, but in every part of the world you have to have a safe plant. And if it goes wrong, they'll benchmark you against what's best technical progress out there. So the Worker Protection Directive is about safeguarding the workers. It's been around since 2003. We have to prepare an explosion protection document. So it's basically saying when you do your risk assessments, like your safety statement, we want it done in a particular way and structured in a particular way. But you can use, it's an overview document, you can use other risk assessments that are there, and you don't have to generate sometimes a whole new set of documentation for it. And again, this directive is stressing that in order priorities, we prevent the explosive atmosphere, we avoid the ignition sources, mitigate the effects of an explosion, and we put in the measures to prevent explosion propagation. Now, the equipment directive is a totally different legislative structure. It comes from these new approach legislation, which is all about free movement of products. So that if you manufacture a chainsaw in the United Kingdom, you can sell it in Germany and Poland and vice versa. You know, it's all about CE marking and having free movement of trade within Europe, and that it meets the minimum safety requirements. So it applies, it was quite radical when it came out because it applied to electrical and non-electrical. This had never been done before anywhere in the world. It was the first time that explosion protection was legislated effectively for non-electrical equipment. And it applied equally to vapors and dusts, even though dusts are a lesser hazard. It's been applicable since July 2003, and hazardous area classification, when you decide what zones you have, and I'll talk about that later, it's simple. The more stringent the zone, the more stringent the design and certification of the equipment. So this new approach directive is like the machinery directive. It's the EU defines essential health and safety requirements. It says don't have sparks within your equipment. Now it leaves the harmonized standards from the European Standard Institutes to tell you actually, you know, what type of gaps and what type of velocities and various metals that you use to ensure you don't get sparks. And then the National Standards Authority, the member states, adopts these EN standards. You know, in UK they're BSEN, in Germany they're DIN EN, and the only difference is that the language is different. And you know what? We are very lucky. If you were an engineer down in or Poland, none of these standards are written in your language. They're only written in English, German, and French. So, I mean, there's a huge amount of information in all of this stuff. But unless your standards authority has a deep pocket and the time and effort to translate it all into your national language, you're in a very tricky position. So we're very fortunate that we actually use English and not Irish. So anyhow, internationally, the International Electrotechnical Commission has developed its own IEC-EX set of standards and its conformity certification scheme. So basically, they took all the good electrical orientated stuff that came out of Europe from 94-9 and all the harmonized standards, and they all put them into this 60079 range of standards. So everything, essentially nearly everything you need to know for ATEX electrical is in this IEC 60079 standard range of standards. And you can use that globally. So if you're an expert in that in Ireland, you can be an expert in that in Singapore, and even now in the United States, or Russia, or wherever you want to be. And in time, the IEC and the International Organization for Standardization, the ISO, are adopting the non-electrical standards that the Europeans developed. And they're going to be global as well. But the Chinese have already jumped on that bandwagon. So they don't have ATEX in China, but they have adopted all the IEC standards, adopted all the European non-electrical standards as mandatory GB codes. So you have to do the same thing. And in Russia, they've done the same thing as well. They just call it GOS, and it's in Cyrillic, but it's the same technical solutions. So basically, the manufacturers can demonstrate compliance with the essential safety requirements. They don't have to follow these harmonized standards, but it's easier to follow them in Europe. And when you do, you get a presumption of conformity. You're presumed to be in compliance with the directive. Now, all of this affects operating companies. Operating companies are not manufacturing equipment, but there's a lot of these standards which relate to good operating practice, such as this one here, this 17 one, 6007917, which tells you how to inspect your electrical equipment, and that you should have a person look at it every 3 years. So if you have ATEX electrical equipment, you'd want to be, have documentation showing that you're actually inspecting it. If you don't and it goes wrong, and you are hauled up in front of a judge, anywhere globally, this is what would be pulled out in front of you. This is the benchmark. So you need to be dipping into these standards and getting familiar with them. Now, unfortunately, they cost about €100 each, but you need to have an awareness of the key ones and to be following them. So if there is, I was just saying it's globally, so if there's a leak of formation of explosive atmospheres followed by ignition and resultant explosion, you'll be benchmarked against all these standards which are now globally. Operating companies and equipment designers have to be aware of the constant pace of development in international standards. So you need to keep dipping into these. So also, I mean, when ATEX came out first, there was a bit of the Y2K about it. People were trying to sell you overly complex solutions. You didn't pull your plant apart. If you had good engineering practice, that really met it, okay, as we will see as you go along. And previous equipment standards like BS codes for electrical equipment, DIN codes for electrical equipment, they're perfectly adequate, provided you maintain the equipment and keep it up to standards. So in many cases, when it all came out, a high specification plant, compliance was generally related to documentation and work practices. You didn't need to pull it apart. Okay, so we look at the flammable and the dust explosion hazards. So the difference, I think you're all fire engineers. I'm preaching to the converted here. You know the triangle. So the only difference is, to get an explosion, you need to have confinement in many cases. Within the equipment, it explodes. And these are the prerequisites for a vapor explosion. You have to have the source leak, air getting in there, and then the ignition source, and away she goes. And what determines when, the key issue that, liquids, what's the hazard? It's the flash point, okay? So when a liquid is gradually heated up until it is just possible to ignite the vapor above its surface, that's the closed cup flash point test. And it's a nice one because it only costs about 150, 200 euros to do. And the GHS system, the Global Harmonized System, classifies liquids as flammable if the flash point is less than 60 degrees C. Now, out in the desert, temperatures can be up in the 40s, but in Ireland, temperatures are only, I don't think they got above 22 or 23 degrees C this year. So really, there are things classified as flammable, but they're not necessarily an explosion risk, depending on the climatic circumstances, whether that happens, you happen to live in Ireland, or you have them inside a building which is air conditioned. So then, combustible liquids such as diesel blends do not form explosive atmospheres. If you throw a match on diesel, it just won't ignite. It's the flashpoint relationship. But if you spray diesel in fine droplets, it can form explosive atmospheres at temperatures below the flash point. So spraying a fine mist is bad news. And this is an ethanol flashpoint curve. We can talk about it in terms of well-known products, okay? Is that if we take whiskey, which is about 44% alcohol, and you go down, you have your flash point at around 25 degrees C, okay? So normally what you do in a bottling line, a big bottling line here in Ireland, is demonstrated. In a small bottling line out in Africa, what we did is with a small modular unit, we cooled the building, small little building, down to about 18 degrees C. The operators love it. So we didn't have to put in complex EX equipment. It's perfectly safe. If you throw a match on whiskey when it's at 18 degrees centigrade, it won't go on fire. Same thing if you take something like a liqueur like Bailey's, the concentration of alcohol is about 17%. So the flash point is up at about 35 degrees C. So if you throw a match on Bailey's, nothing will happen. And the same with beer. But if you were to actually put beer, which is about, high-strength beer in the brewery is about 7% alcohol, and you put it through a pasteurizer at 70 degrees C, and it starts to leak out and spray at that temperature, and as an ignition source, the beer will actually go on fire. So there's this temperature relationship which is quite important to realise. And the EU Commission has taken the old rule of thumb from the German EX regulations. Basically is that if it's a pure substance, or basically a well-controlled substance like alcohol and water, the safety margin is about 5 degrees. While if you had a blend, with diesel which changes during the year, or somebody could get a little bit of petrol in it or whatever, you'd want to have a wider margin. So if it comes back to this GHS classification, in the desert the temperatures could reach 45 degrees C. Add 15, that's why the thing is classified as flammable if the flash point is less than 60 degrees C. But if you maintain these margins, it's inherent safety. And that's what we want to do from the starting point, is inherent safety. It's always simpler. It's to avoid the formation of flammable atmospheres. So again, what is a hazardous area? Hazardous area is one that's really going to, special precautions are necessary. And why are special precautions necessary is because it can injure you. So if you take 10 litres of explosive atmospheres, so that's about 20 bottles the size of this, full of air with solvent in it in the explosive range. So it's atmospheres, not liquid, it's atmospheres. So if you have 10 litres of explosive atmospheres, and that goes bang, that's going to hurt you. That's a hazardous potential explosive atmosphere. But at the same time, if you put liquid, you have a liquid drum, and you don't create the atmosphere, it's in a sealed drum, it's not hazardous. So it's this, concept that you have an atmosphere which is in the explosive range, which is more than 10 litres, and it can ignite it, it can hurt you. So I came across this in a Swiss guidance, and I actually have to do the sums myself from scratch. I'd be too lazy to do it. But basically, what's the energy release when 10 litres of explosive atmospheres goes bang? And they say it's about 10 kilojoules of energy, which is the same as if a 10 kilogram weight fell 100 metres and hit you. And I wouldn't like that. I wouldn't like that at all. So then you do some easy sums. The lower explosion limit of ethanol is 3.1% by volume. So 10 litres of explosive atmospheres. You could create 10 litres of explosive atmospheres with 0.6 of a gram of our favorite product, ethanol. So it doesn't take much. So the good lady spraying her hair will want to make sure she's not actually smoking at the same time or spraying too much. But anyhow, the dust explosion, again, I mean, the dust explosion is based around, I mean, a lot of things is sort of carbonaceous and will burn, whether it's wood or grain or sugar. You into an explosive, a thick cloud, you have an ignition source, it just goes bang. Now, there's a little bit more complexity on that, dust explosions, because most of the time they don't happen, they're not as we underestimate them because they don't happen so regularly. But they do, I mean, there's been quite a large number of them recorded. I mean, the German safety officials say that 600 dust explosions over 25 years, which they estimate is less than 10% of the total. And for the other classification, which includes the chemical industry, the ignition, the source of ignition is usually mechanical and electrostatics. And then mills. Mills are a big problem. 18% of the explosions occurred in mills. So why did it explode? Well, the likelihood is that a fire in a dust layer will occur rather than a dust cloud explosion. The likelihood is that you get a smoldering fire. But if the dust layer is lifted up into a cloud, it will just go bang as an explosion. So it's the first little ignition, the first fire, then something lifts up the dust that's lying there, and then you get bang and it just rips through the building. And I know there was, I don't know the details, but there was a rubber crumb factory up in Drogheda, Dundalk, about 4 or 5 years ago. And flashback, and 4 people, 2 firemen and 2 operators ended up in James's Street in the severe burns unit. And I don't know the details, but I could guess that, as you will see, is that the fire was smouldering. They hit it with a jet of water, lifted up and exploded back on them. So the rule number 1 is never ever create a dust cloud, and don't leave the layers lying around there because they have the potential to create a dust cloud. And this was a famous one. I mean, if quite a few have happened. This was in Blaye in France. I mean, these are the silos you see down near Google, down the Grand Canal dock, which are built, like concrete fortresses. But when the dust explosion initiates in a fan, it rips through the building from one section along the dust layers, and the whole thing just comes tumbling down. I mean, it can be very, very destructive. And I mean, there was a similar event in Bremen about 2 or 3 years before, and it led to a lot of research done in Germany on the whole issues of dust explosion. So for many organic materials, the lower explosion limit is 10 to 50 grams per meter cubed. What does that mean? You mean it's a lot more. We were talking about milligrams with the alcohol, but this is grams. And this is, well over 100 times the exposure level that you would have somebody working it. Because general dust exposure level, for health is 10 milligrams per meter cubed. So it's a big, thick, dense fog. You wouldn't be able to see a light 2 meters away. But at the same time, if you have a layer of flour 0.3 millimeters thick on the floor, it can, in principle, fill a 3 meter high standard building with that explosible dust cloud. So if we just have this as an example, there's So the bottom line is, don't go stirring up clouds, as we talk about, is use a vacuum cleaner which sucks it up, And then a dust cloud is an immediate explosion hazard, but every dust layer is a potential dust cloud. And here's another this is a silo, tiny little silo, dust at the bottom of it. And you'll see it lifted up, and it's actually a thick cloud, and then it's ignited. So it's quite thick. This is from a Swiss studio, so you don't have to hear the German voices. Anyhow, should ignite. Yeah. And it's violent. Yeah. Okay. So intuition is a good guide to flammable properties of liquids. I mean, they always smell kind of, alcohol-y or solventy. You know from sniffing them whether they're nasty or not, okay, generally. But intuition is a really bad friend with dust. I mean, lots of things go bang when they're in the right format. Milk powder, coffee, aluminium powder, flour, grain, aspirin. So it's normally necessary to test a powder in a specialist laboratory. If you want to get an explosion, you won't get it with lumps. The particle size has to be less than 0.5 millimeter. But if you have 2 or 3% or even 2% of the material in that range, the whole thing will go bang. Okay? And the moisture content has to be about greater than 25%, because when it's greater than about 25%, it doesn't, be held in suspension so well. And it's weak or no explosive properties. As you start going up to about 30-40% moisture, it won't. Or even if you had fat content, like in chocolate. Dry chocolate powder will go bang, but chocolate crumb, which has a fat added to it, won't. So dust properties depend on the processing conditions. The finer dust is explosive. So, conditions depends on the performance of the equipment, whether you use mills, whether you have abrasion in conveyors, etc. And the dust explosion testing, it's about $7,000 to send it off to a laboratory. And that's only the start of it. If you're in the pharmaceutical industry and you need to send a kilo of your development product, which is getting ready for trials, that kilo of development product is probably worth about £1 million, and you're sending it off to some guy in the UK or somewhere to blow it up. So anyhow, fortunately there is a database out there. I think it's now up to 4,600 samples. So you can find a lot of things like foodstuffs and regular sort of binding materials that you use in tableting and various other things there. Which is quite good. Saves you a lot of money, for orientation purposes. And it's supported by the European Commission now. Okay, so that's a little bit about dust and flammable hazards. So again, the protective measures now we'll go through: avoid the explosive atmospheres, seal the equipment, keep the plant clean. We avoid the ignition sources. We have our ATEX certified equipment for areas zoned as hazardous. We have our constructional explosion protection, which is if we can't stop it exploding, we make it explosion resistant construction. We put in explosion venting, suppression systems or isolation systems. And then we have these measures to stop the explosion propagating between the equipment items. So that's what that's what we try and do, okay? So how do we avoid the explosive atmospheres? Now, you have an obligation to do this, okay? Can you process with a higher, hydrocarbon with a low flash point with one that has a higher flash point? There's a lot of things that can be done when people actually challenge themselves. Keeping things cooler rather than hotter keeps them out of the explosive range. If you have a dust, if you have a larger grain size, therefore reduce the extent of the flammable atmosphere. Or, keeping it a bit moist. Why do you need it bone dry and milled to a very, very fine level? So the avoidance of explosive atmospheres, the inerting, a lot of us in the chemical industry would know this. We use nitrogen on vessels, centrifuges, dryers. We have oxygen analyzers, we have sweeps, and we have oxygen limits and procedures which must be adhered to. And in coal mills they do it. They put the flue gas, which is rich in carbon dioxide, back into the mill to keep it inert and to keep it out of the explosive range. They also, you can also add inert solids to combustible solids, but sometimes you have to add about 70-80% inert to a combustible solid to take it out of range. And the mining industry uses this a lot. How on earth do you stop dust explosions in a coal mine? There's so much dust around. You'll never stop the dust being there in a confined space. So what you actually use, you put down limestone around the place. And if there's enough limestone in the mixture of dust lying on the floor and the equipment, and it's about 70 to 80%, then that mixture won't ignite when it's lifted up. So it can be done. But you make sure you have enough limestone. So there are guidance on EN guidance documents from CEN, the European standards on how to inert your centrifuges and how to set it all up. So again, follow the scripture, go research, see what's already proven, and stick to it. So adapt to technical progress. I mean, there's no excuse anymore. I mean, dirty, fittings around the place. I'm sick and tired of telling people, that Jubilee clips with rubber hoses that you make up yourself are acceptable. And the amount of dirt that ends up around them. I mean, there's proper fittings. They cost a little bit more, but the area is spotless. I mean, we can design a plant that we don't have layers of dust lying around it. If you go to a pharmaceutical plant, you don't want to see pharmaceutical dust lying around the place. It's unhealthy. But there's no reason in a food plant anymore that it should have, that amount of dust lying around vessels and things like that. We've moved on. It's called adapting to technical progress. Ventilation, I mean, particularly with flammable vapors, can reduce the local concentration and the extent of the hazardous area. Ventilation equipment, local extract arms must be maintained in good condition. So, I mean, there's standard approaches. I mean, normally normally the vapors we're dealing with are heavier than air. So you basically pull out at the bottom and push in at the top. And you can put in gas detectors, to alert you if there's a flammable vapor building up in the space. So housekeeping. So ventilation takes away vapors. Housekeeping for dust explosions. That's the mantra, the three things. So if you keep it all sealed up and you clean it, okay, I mean, you might have a little spill, but every now and again something goes wrong. But if the layer is not there for longer than a shift, the area is not hazardous. So if you don't have a persistent layer for longer than a shift, and this is in the IEC-EN standards for classification, it's not a dust hazard. So persistent layers can lead to a dust hazard with a cloud and an explosion. But if they're not persistent, keep it clean. You don't have to spend all that money ATEX rating the externals of your plant. So again, when you're cleaning it up, don't use brushes, use a vacuum cleaner and suck it up. So we've done all those measures to, as much as possible prevent the explosive atmospheres from occurring. So now we look at, well, if we can't always avoid them, we have the zones, okay? And the whole idea is the zone is that the more stringent the zone, the more advanced and developed the protection measure it is. And we have to designate the zoned areas by warning signs, and we have to have hazardous area markings, and we have to have hazardous area drawings. But as I said to you, I could design a plant pumping solvents and ethanol now with no external zones. Wouldn't cost a whole lot more. It can be done. And it would save you all that complexity, inspecting it every 3 years and everything. So the three zones we have for flammables, the zone 0 is where the gas, vapor, or mist is present continuously for long periods or frequently, which is generally seen as greater than 1,000 hours out of 8,700 hours. And the zone 1 is where it is likely to occur in normal operation occasionally, which sometimes we use the rule of thumb between 10 and 1,000 hours. And then zone 2 is where it doesn't really occur unless something goes wrong and we have a failure, and it will only be a short period only. And that would be less than 10 hours a year. And we don't get excited about catastrophic failures. Vessels rupturing, pipelines splitting in two, the concept of ATEX. Okay, and then we have the same thing with the dusts, is that 2.0 is where we have the dust cloud, and look at the word there, it's cloud, okay? It's cloud. That's this big thick cloud, has to be there continuously. And the only place we get that is inside equipment. And then 2.1 is where it can occur during normal operation occasionally, something like going down a chute from one vessel to another. And then 2.2 is where we have a combustible dust in the air is not likely to occur in normal operation, but if it does occur, will persist for a short time only. And again, it's a cloud, okay? And the are not an explosion hazard, but are a potential explosion hazard. And that's the interface. If they're persistent, we drive ourselves into the 2.2 classification, but only when they're persistent. So, I mean, this is the classic example of a tank with flammable liquid. Zone 0, it's a volatile liquid. There's no ventilation there. Zone 0 inside the tank. Zone 1 where the tank is venting when the road tanker is filling it up and we're pushing the vapors out. And then zone 2, well, I mean, if the vapors are coming out the top, they can sink down around the side, or the pumps could leak in the bund, and we give it more or less a zone 2 classification around it. Now, the zoning for dust, I mean, the Germans are very good. They have a lot of guidance. This is one of their ATEX guidance for bakeries. Now, you see there, I mean, it's nothing modern, sexy, new. And quite potentially, you could drive a fork truck into that bag and spill it. But if you clean it up, it's not a problem. Okay? So it's reasonably clean. There's probably the odd spot of dust here or there. It's reasonably clean. That's a no zone. So don't go spending a huge amount of money EX rating trucks and lights and everything for that. Now this is where you have an old style plant, leaks of dust. You know, it's visible around the place. That's a zone 22. Yeah. Okay. So how do we, I mean, we know the theory, we know what the zones are, but the issue is, how do we assign them? How big should they be? And, you know, which code do we use? Because there's a methodology in the IEC codes, one for gas and dust, but they don't actually give you a lot of worked examples, and some of the examples are a bit misleading. So there is a Institute of Petroleum, or is Energy Institute code, which has been around and used in the UK, but it's very orientated towards oil refineries. We don't have those really in Ireland. We've, you know, smaller scale facilities, and they have calculation methods, you know, which are all very fine, but they all work on the basis that you know how big the hole is when it's going to leak. I mean, we don't have a clairvoyant ball. There's a nice code there, which if any of you are working in sort of, you know, buildings and boiler systems, very nice code there from the UK Institute of Gas Engineers and Managers, very practical for gas installations, low pressure gas systems, uses the concept of zones of negligible extent in most cases. I strongly recommend that if you're doing any gas work, you know, around buildings, that you follow that. The Germans have, for more than 30, 40 years, have their statutory accident insurers, have the chemical industry, and a very, very extensive set of worked examples for gases, liquids and dusts. It's unfortunately only in German only. Some of it is pictorial. There's a book where somebody's done about 114 examples sketched up. There's one for flute bed, simple flute bed dryer. Personally, because I speak German and we worked it, is a German one is the best. It works for everything from drums to oil refineries. And some of it is now, the latest edition of it, a little bit of it is starting to appear in English. So, I mean, there's 40 years of experience, 50 years of experience gone into it. They were way ahead of the game before anybody else. Okay, so now that we have our zones, we have to avoid the ignition sources. Well, there are actually 13 different ignition sources defined. Hot surfaces, flames and hot gases, mechanically generated sparks, electrical apparatus, stray electrical currents, that kind of doesn't come up very much, static, lightning, simple enough to deal with. And then these are sort of wobblers about electromagnetic fields, radiation, ionizing radiation. Yes, if you had a tank farm in Dublin Port and a ship came by with a big radar system running, it could actually ignite a vapor. So it's best not to have the vapor hanging around the explosive range. Ultrasonics, yeah. Adiabatic compression, well, that's what happens in a Volkswagen diesel car. And chemical reaction actually happens quite a lot because a lot of things decompose under heat and weight. Like a peat stack or cold stack will self-decompose and go on fire. Or in a milk dryer, the lump of milk the lump of milk powder will get bigger and bigger and self-ignite. So we have that quite a bit, this self-ignition occurring. But of the 13, there's probably only 6 that we really have to, deal with on a day-to-day basis. So, I mean, they're the key ones: the hot surfaces, the electrostatic discharges, the flames, the electrical connections, and the mechanically generated sparks. Okay. And some pretty pictures horror stories, lights being shoved down into vessels to have a look to see what the level of powder is, cigarette butts, layers coming apart. None of this 3 years inspection to IEC, 6 years, 9, 17 there. Somebody doing a bit of welding where they shouldn't be doing. Okay, so once an area is zoned, only equipment certified for that zone or more stringent zone can be used. And this applies to electrical and non-electrical equipment, where previously older standards related to electrical equipment only. So you can bring in some maintenance equipment under a hot work permit. And with a few exceptions, you can bring non-certified fork trucks, or you can bring trucks into a tank farm to unload flammable petrol or whatever into the tanks adjacent to it. But the bottom line is, once you zone an area, it's going to cost you big money. I mean, if you talk to the electrical engineers, they'll tell you that the difference between doing an ATEX electrical installation versus an ordinary one is something like a factor of 3 or 4. It's big money. So, it's worth spending the money on getting a proper flexible connection and throwing out the Jubilee clip with the rubber hose that you made up yourself. Not to mention that you have to go around and do the paperwork every 3 years. So anyhow, this is where it gets confusing, is where we have zone 0, we have category 1 equipment. And I don't know why, if they said 0, why didn't it have 0 there? They could have made it simpler. They deliberately went out to confuse people. So 0, category 1, G for gas, which is the most stringent equipment. Zone 1, you can use the most stringent one, or you can use less stringent one, which is 2G equipment. And zone 2, it's 1G, 2G, or 3G equipment. And then in zone 2.0, it's the same. It's just a 0 with a G, it's D for dust. And category 2.1, category 1D, or 2D, and so on. Okay? And the IEC, system, same technical standards, same solutions, but they now call it GA, GAGB, GAGB, GC, DA, DA, DB, DAB, and C. It's actually less confusing. It's more logical. But there's no reason why you can't. In Europe we're meant to have the CE mark, but there's no difference between the IEC EX equipment used internationally and the European equipment anymore. So what is Category 1? Well, Category 1 means that you have to have the necessary level of protection, even in the event of rare instances related to equipment. So the rare faults, like the agitator in the vessel starts to work totally loose and swing from side to side and wang against the side of the vessel and scrape against it. I mean, they're weird and wonderful. And you have to have 2 levels of protection to ensure that if you have 2 levels of fault. So it gets very complex. Category 2, you only have to think of frequently occurring disturbances or equipment faults, something that the lubrication fails. But you don't have the weird and wonderful that the agitator swings wildly and hits against the side of the vessel. And it's 1 level of protection. And Category 3 is the requisite level of protection during normal operation. So it's 1 level of protection based on normal operation. So it's just more or less standard. It doesn't have sparks and ignition sources in normal operation. And so Category 3, you only have to consider faults in normal operation. Nothing special or expensive. Vendors can self-certify. Category 2, faults related to frequent disturbance have to be considered. Starts to get a bit more complex. Vendors can self-certify non-electrical equipment, but need a notified body for electrical equipment. They have to go and get it approved for electrical equipment. I'll explain why in a few minutes, because electrical equipment is more complex. So Category 1 equipment is horribly expensive. It's often 7 times more expensive than Category 3. If you want to get a Category 1 fan, it could cost you 7 times more than a Category 3 fan. That's a lot more money. So really, get your process engineers and your engineers to design out these Zone 0 or 2.0 areas, because you start saving yourself money when you look at simple solutions and avoiding the hazard at source. It also makes it inherently safe. And you can look at these slides afterwards. There's all this marking and where you see where the categories are. I could spend an hour going through this section alone.
What was the instrumentation you said? Where?
Oh yeah, the Category 1 equipment is horribly expensive. I mean for, you know, motors, fans and things like that. Instrumentation has very little energy sources in it, so it's not difficult for them to do it. Okay, but for other things, it's like if you had a vessel full of solvent with an agitator, and you wanted to get certified for Category 1 for a Zone 0 inside, it would cost you an awful lot of money. So if you put a nitrogen blanket on that vessel and you change the Zone 0 to a Zone 1 or 2, you could put in a standard agitator, which would be less than half the amount of money. So you'd have a safer plant, and it's cheaper to buy nitrogen to have really complex, expensive agitators with all these sensors on them and things like that. Does that make sense? Yeah. The electrical equipment, it's all very defined in this IEC 60079 series of standards, but you have to follow it rigorously. So it's not a question of buying something, the motor with the cert. You have to install it right, you have to commission it right, you have to maintain it right, you have to tighten it up right on the enclosures and all of these. So that's where the costs start and complexities start to mount. And I'll just go through, you know, some limited amount example protection types very briefly for electrical. I mean, a common type is the increased safety, which if you were to look up at these lights and they were to be EX, you could buy them as EX lights. And they're basically, you know, they cost you more, but you'd wire them up relatively the same. And they're based around the fact that somebody has engineered out the sparks and arcs within them. And they're good for Zone 2 or Zone 1 in many cases. And that would be, you know, what's widely used now for, you know, luminaires and for some type of motors. The next type is instrumentation, because what you do with the instrumentation is that you have it intrinsically safe, which means that there's not enough energy in the field to create a spark. And you don't need a lot of electrical energy for instrumentation, but you have to wire it up correctly, barriers in the cabinet, and there's quite a lot of complexity in designing these circuits correctly. But buying the actual piece of kit, the EX transmitter for measuring temperature, is not a whole lot more than buying a standard temperature transmitter. But the complexity is designing the circuit and getting it certified and wired up. The next one is the flame proof, which is the traditional one going back 100 years, is you basically put it in a box which is robust, and if the gas comes in through the gap, ignites, the flame is cooled, goes out the gap here so that you don't get propagation of the explosion outside. But the real key issue here is that you don't over tighten or under tighten or paint over these gaps. But that's the traditional manner that we used to use for many years, and still for heavy motors you'll find it. Now, what's non-electrical equipment? Well, a final product assembled using both electrical and mechanical elements may not require assessment as electrical equipment, provided a combination does not lead to additional ignition hazards for this assembly. So if we take a motor and a pump, that is not electrical equipment, provided we're not creating any additional hazards, because we got our cert for the electrics and we're not altering it or anything, okay? So if you make an assembly with electric motors, pumps, conveyors, etc., you can call it non-electrical equipment, and you can self-certify for Category 3 and Category 2, which are, you know, 2 out of the 3 categories. So a manufacturer can do that himself, and that's normally what happens. So how do we go about certifying non-electrical equipment? So, I mean, the national standards for electrical equipment, the DIN standards, the BS standards, were all there prior to ATEX. However, there was no equivalent process or standards in place for non-electrical equipment. And certainly a lot of people went around knocking on the door, pulling the old Y2K trick on a lot of people, you know? But the reality was that for years, okay, you know, common mechanical equipment was performing day in, day out without malfunctions and not producing ignition sources. I mean, fans, the blades don't whack off the casing and spark. We know how to design them so they don't do that. Okay? So with electrical equipment, there's always present, active ignition sources. But with non-electrical equipment, generally speaking, the ignition sources are not there. So that's why we don't have to jump through so many hoops when it's non-electrical equipment. Okay? And then, even where malfunctions have to be considered, such as for mechanical equipment can meet the requirements of Category 2 equipment, which is where you have to consider expected malfunctions. By just being a bit of care and attention and making sure the bearings don't run too hot, etc., we can certify it. Okay? So the electrical equipment, in summary, it's associated with inherent ignition sources, while the non-electrical equipment is not generally associated with inherent ignition sources. So the typical approach with non-electrical equipment is we go through the documentation, we do our assessments to demonstrate that we're not going to get these ignition sources as being effective. So we have our 13 sources, and we go through them one by one and see where we lie. And there's a methodology, there's a standard. I mean, there's an EN standard how to go through the methodology, and you decide, do we need to consider, depending on the category, consider normal operation, expected malfunctions, or rare malfunctions, and then we go through the 13 different ignition sources, and we decide whether we have them or not. And if we have them, we can do a few tricks, as I'll explain. So there are EN standards which help you there. There's a thing called constructional safety, which has a little C, which basically means that the things that the bearings, tells you how to design the bearings so they don't overheat, tells you how to design your lubrication systems. This type of thing, simple things like that. Clutches, stuff like that, so they don't create sparks. Now, we can also put sensors on, which is, if something could run hot, like the lube oil could be an expected malfunction that the lubrication fails, we could put a sensor on to detect it running too hot and shut it down, or a level sensor. Now, that's all we need to ever do. There's all these fancy standards, like what we had for, electrical equipment, sort of, flame-proof enclosures. You can do that, but you never really have to. I mean, normally by constructional safety and controlling the ignition sources, putting a few sensors on it, you can get where you want to be. And we have standards also, related to non-electrical equipment for explosion relief, for vents, explosion suppression systems, and explosion isolation systems. Static implications. Static is the only one that is actually mentioned directly in the directive, because it happens a lot. So it's the only ignition source that it actually tells you, you have to deal with this particularly. And workers must be provided with appropriate clothes which do not give rise to electrostatic discharges that can ignite the explosive atmospheres. So that's in the Worker Protection Directive. So if I was to walk across this carpet and I was to touch the doorknob over there and I got a little electrostatic shock, well, the largest that those electrostatic discharge amount to is about 4 millijoules. But flammable solvents are ignited by less than 1 millijoule. So it's going to go bang with a flammable solvent. So small electrostatic discharges will ignite all common solvents at or above their flash point. In general, so with equipment, vessels, pipes, and etc., we have to have a resistance to earth of less than 10 to the 6 ohms. Now, there's not a lot of energy in the electrostatics. So 10 to the 6 ohms is 1 mega ohm. So that's easy to do, provided you don't put plastics and non-conductives into your plant. So the international standards, there's a good one out there now, into 60079 It says in zone 0s and 1 that the footwear and flooring should not exceed 10 to the 8 ohms, which is what's called dissipative, okay, or in common lingo, anti-static. And that was never a problem in the old days. We had concrete floors and people walked around in safety boots. Now they go around pharmaceutical plants with resin floors and booties. It's a disaster waiting to happen, and they bring in solvents as well, For dust, the same applies for zone 20, but nobody works in a zone 20, okay? And zone 21, ignition energy is less than 10 millijoules. When we have a particularly ignition-sensitive powder, we need to start taking those precautions for footwear and flooring. And, you just need to be careful when people are putting overshoes on, rubber booties or plastic overshoes or working at height. But look at it here, okay, is that for zone 2 or zone 22, if we keep the hazard down, we don't have to take additional measures. So you start saving yourself money by not having these high-risk zones in the external area. And then with flexible big bags, you know, we need to be careful with these, because what we can get is what's called a propagating brush discharge. You can be discharging this through the wrong type of bag, and the whole thing will explode on you, the dust, the powder. So there's 4 different types of FIBCs, A, B, C, and D. A is only to be used when there's no explosive atmospheres around. But frequently, I mean, you do find people using the wrong type of big bag, and it's an accident waiting to happen. And it's the same principle applies to plastic drum liners when you're chucking powders out of a drum which has a plastic liner on it. And then, I mean, we know all of this. I mean, when you're handling drums or you know, metal or plastic IBCs, and plastic ones should be conductive or dissipative. It's essential to use the correct earthing straps, and the same with hoses. You have to use, you know, the metal braided hose, or the, you know, that has the earthing measures with it, because if you don't follow these correct earthing procedures, it could lead to ignition. Okay, we're coming towards the end now. The constructional explosion protection. Sometimes you can't avoid the explosive atmosphere and ignition source. I mean, with a dryer, you can never say that you won't get ignition, because you can get these self-ignition and glowing nests. And then with high-speed mill, I mean, a bit of metal could break loose, or a bit of tramp metal could get in, and you could get a spark.
Sorry, can you explain the glowing nest?
The glowing nest is what happens is if you get a layer that gets thicker and thicker and thicker, it will start to self-combust at elevated temperatures. Okay, and it happens in dryers, milk dryers. It happens in roaster systems. It happens. I mean, you could even have it in a coal yard or peat yard where you have, you know, 6 or 7 meters high stack of coal, and the coal is, you know, down at the low level, and the compression and a bit of moisture, it starts to self-decompose. It's spontaneous combustion, yeah. And what happens is that little glowing nest will break loose and get swept along through the dryer, and then it drops into the silo, and suddenly it's there in a cloud with air around it, and the whole silo goes bang. Yeah. Yeah. So you can never say that with a drying system, you know. You can never say that you won't get one of these. So you can't say that, you know, you have a zone 20 in a spray dryer because you have that constant powder falling there, and you can never say 13 different ignition sources will never happen. So that means that you basically have to start with these, you know, have to add on these constructional explosion protection measures. Now, what we do say, I mean, with electrostatics, okay, is if that the minimum ignition energy is greater than 10 millijoules, okay, well then these ubiquitous, you know, leftover, never could be ruled out, tiny sparks are not going to ignite the powder. So if the powder is above 10 millijoules, rely on what's called as rigorous avoidance of ignition sources without having to go and put explosion panels on silos and things like that, provided we don't have glowing nests, provided we can eliminate the 13, which is a glowing nest. But, if, you know, that would be the case where you're transferring powders which are not being heated. Yeah. And these constructional explosion protection measures, I mean, you can either build it to take a 10-bar force, to take the force of the explosion, and you kind of do that when you have toxic pharmaceuticals. You don't want to be spraying neighbors. Or you can have explosion vents. We know these in milk spray dryers and various other things. Or you could put suppression bottles, which, you know, an electronic sensor detects the start of an explosion and immediately fires the suppressant, you know, material to stop the explosion developing any further. So you only get maybe 0.2 or 0.3 of a bar of pressure, and it's only a small explosion, and that can be held within the mechanics of the vessel. So when you do vent these explosion vents, I mean, the stuff is being chucked out at enormous force, it's smouldering and burning, it reaches into a lovely bit of air, and it has a secondary explosion as it exits the vent. So if you were to have a building nearby an explosion vent, you could basically do severe damage to that building. So you have to be careful that when these things go, there has to be ideally a vertical, because you don't want to have any body, you don't want to have any combustible material, and you don't want to have any buildings in the way when these things go bang. And the people sometimes forget that. I mean, they have them discharging out the side of the building, and they build another building just across the road from it. Not a good idea. Then the final part of ATEX is that they say is that we need measures to prevent the avoidance of ignition, so mitigation of exposure where necessary, and that's what the legislation says. Where necessary, be combined or supplemented with measures against the propagation of explosion. Because if it goes bang in the vessel, it's going to accelerate down the pipe, increase up to a detonation, supersonic speed, and basically damage the next vessel down from it. So you get this domino effect going from one vessel to another, and we don't want that to happen, obviously. So for gases, we use what's called flame arresters, which are metal, special designed metal of about 0.2 of a millimeter or even smaller, gaps between them, which quench the flame as it's true. Now, that wouldn't work for dust because you just block it straight away. So it's a bit more complex for dust. With dust, we can buy ATEX certified rotary valves, and these are rotating around. And we normally have two vanes always sealed against the casing, and the gap here is less than 0.2 of a millimeter, and you want to make sure that that doesn't wear down. And if you get an explosion in the vessel, it gets quenched as it goes through that gap, and that rotary valve stops the explosion propagating from the vessel to the next one. We can do this with suppression bottles. We can have a detector, and we fire the suppressant in the conveyor or in the pipe or whatever to stop the explosion progressing. We can put slam shut valves. You often see this on flue bed dryers. The inlet air, the air handling units, the heating systems will have a slam shut valve separating it from the chamber where the actual drying is going on. So you don't want the explosion going back, blowing apart all your heat exchangers and everything. There's some funny ones. I've never actually seen them. There's something like discs which spin and close. Under normal velocity it goes through. High velocity just spins and close. There's another variation of it where you use a bottle and a detector to inject the gas and spin it faster in advance. Never seen one of those. These ones are what the Germans call explosion schlots or explosion ducts. Basically, if you had a filter here and you had an explosion in the filter, you didn't want the explosion to travel backwards into your equipment, it would just basically blow out of the relief valve here, and under normal circumstances it would just go through slowly and do a 180 degrees and go back down again. They're not certified to give 100% protection, but there is now a design of that and a standard, and some people are making them ATEX certified, which will give you the necessary level. But they're only in the market in the last year or two to give you that, guarantee of protection. So the technology relating to constructive and exposure propagation measures, it's only relatively recent established. I mean, if you take a plant that was built in the 1950s, you can't pull it apart, okay? I mean, with conveyors and silos and everything. It's always, about what's, appropriate. It's a bit like the modern car comes with airbags, but how many airbags? I mean, you have to install the seat belts and the braking systems and operate the plant properly with the old one. But whether you put all the airbags in is, it's here or there. I mean, it's risk appropriate. If you can do it with a reasonable amount of expenditure, you should do it. But if it means pulling apart a plant totally, you may not do it. I mean, it has to be a sense of realism. Organizational measures. I mean, I think you all know this. I mean, we need to keep this explosion protection document up to date. It's an overview document. You can refer to it or risk assessments, but you have to have one. If anything goes wrong and you don't have a decent explosion protection document, you're basically for the high jump. So you have to have work procedures, training of staff, hot work permits, warning signs, coordination duties between contractors. And I mean, the biggest issue, as we all know from safety, is culture. If you have a dirty plant, it's going to be a bit of a culture change to change the plant. But if you start off with a new plant and it's clean, it should remain that way going forward. I mean, organizational measures, you know, signposting, operating instructions, training. Operating instructions must govern the behavior of employees during normal operation in the case of malfunction. Responsibilities must be defined. I mean, this is all standard stuff. Monitoring and maintenance, I mean, you have a maintenance schedule. If a vendor sells you a piece of non-electrical equipment and gives you key maintenance routines and you don't adhere to them, well then you're for the high jump, he's not for the high jump if something goes wrong. You have to sort of adhere to what he's telling you and his safe instructions for use. The necessary protective clothing, you know, the necessary shoes, the anti-static precautions with your clothing, cleaning on regular intervals, but after, you know, maintenance work where you'd be opening up dryers and having dust around the place. You know, zones have to be clearly marked. So, and then, you know, if you have an area where there's explosion venting, make sure you don't have people walking around there on a regular basis. Okay, under maintenance it might happen, but you know, you have to be careful not to have regular traffic going through areas where there's explosion vents. Coordination duties, you know, the explosion protection document has to be coordinated with your contractors who come on site. This is standard stuff again with, you know, general health and safety. So there you are. I mean, ATEX is more comprehensive than previous regulations, particularly because it brought in dusts and non-electrical equipment. So companies must be now compliant. I mean, it's in about a decade now. Equipment must comply with the hazardous zones. The work procedures must address the hazardous training. And then outside the EU, I mean, people are going to be benchmarked against the same technical standards. It has to have the same plant, safe plant.
Thank you very much.
Did I put you all to sleep?
No, I think you were absolutely whizzing along there. I get the sense that this is you're only skimming the surface of that. This is a very, very, I suppose, complicated subject and topic. Thanks very much. Has anybody any questions? Sorry, I'm just going to get you the microphone.
Do you want to get the microphone? Yeah.
Pat, excellent overview. The question on the ethanol facility, the drinks facility in Africa, you spoke about the cooling and bringing down the zoning using, bringing down the temperature of the environment. But surely, if you didn't have redundancy in your systems, you have a potential problem if there was a failure.
Yeah. Yeah, but I mean, we have systems which will automatically shut it down if the liquid temperature or the air temperature goes too high. I mean, it's not a big facility; it's kind of modular, built into a number of 40-foot containers. but I mean, the gas thing about it is that the operators absolutely love it. When it's 19 degrees outside and it's 19 degrees centigrade in that building, they are delighted and they keep the doors closed.
Yeah, exactly.
Yeah.
I'm sure. And so no, it was important to just clarify that.
Yeah. And there is actually sensors in you know, that if the vapor gets out, there's another level is that they'll trip the whole thing down. But it means that in an environment where it would not just be possible to have people maintaining very complex equipment, we can come up with something a lot simpler. Yeah.
Pat, thanks for a good presentation. Paddy Sheridan, Oriflame. My question is, do the regulations stipulate who can and should establish the zoning?
Yeah, the issue here, I mean, we have a common law system in UK and Ireland where ultimately we're not prescriptive compared to the civil law tradition in continental Europe, Okay, so everything is allowed until it's written that it's not allowed, and ultimately the judge is the final arbitrator. So are you competent or not? Well, it's when you're hauled into court and the judge decides. Okay, the state here is not going to write legislation in terms of typically is competent. But there is other places. The Germans have sort of specified how many years training you need to have different levels of competency in their regulations. And we now have a minimum level of competency. It basically says to inspect the equipment you should be competent. And in the UK, private training and a private sort of type scheme called Compex. And that's good for people who are inspecting equipment out in the field, like an advanced electrical person. But under the IEC EX scheme, there is now a super level of competency where you can get certified to be engineering systems and design them off, and that will be going forward what will be, at the top level recognized, whether you're in China, anywhere in the world. So if you wanted to be, absolutely 100% sure, and you had that and you threw it in front of the judge here in Ireland, he wouldn't have any comeback to say anything else against it. Yeah.
So just on that point, EN 60079-14
Yeah.
ATEX
Yeah.
makes very, and that's a statutory instrument in Irish law.
Yeah.
And it makes very definitive requirements for both the responsible person,
Yeah.
designer, and the technician.
Well, it's a standard, which is an Irish standard, but I don't think it's actually a statutory instrument per se, but certainly it would be, the judge would look at it as what is technical progress and what is best practice out there, It's not written as an Irish technical regulation.
Correct, but where you get into is SI 299, then it refers to the best appropriate standard, which is for Irish, because we've an IS standard for it.
Yeah.
It's EN 1600.
Yeah. So it's an indirect relationship. Yeah. While other jurisdictions have actually written in a technical regulation on what your competency is. Yeah.
Any more questions? I have one myself. Could you tell us a bit more about the danger from, you mentioned ship's radar igniting oil installations?
Yeah.
Are you dependent on something like a coil or a loop or something like that?
Well, there's different ignition sources there, and there's one of them electromagnetic radiation. So in fact, the electromagnetic radiation of a ship's radar is actually capable of being an ignition source. Now, there was a paper written, I think, for the ICME on it. Somebody had done it. If you sort of Google around, you will actually find it, and the radius or whatever. So somebody's done the sums on it. Yeah. But I mean, it comes back to the point is if you don't have the stuff out there outside of the equipment in the hazardous zone, you shouldn't really have to worry about it, Yeah.
I've seen where ship's radar is believed to have created havoc with instrumentation systems that weren't adequately screened.
Yeah.
It's not quite the same thing, but it's similar.
Yeah.
And those would have been intrinsically safe systems on oil tanks.
Yeah.
So.
Yeah. Yeah.
In the UK, on some of the ports, and particularly in Aberdeen and Northern Grimsby, there's actually requirements that the pilots won't enter the ship until the radars are being produced. For that very reason, when refineries are...
Yeah.
Well, thank you very much, Pat, for your presentation. You might show your appreciation in the normal way.